The subsurface environment consists of up to 3 different phases, namely soil, water, and air. When an environmental contaminant enters the subsurface, it may transport within a single phase driven by diffusion, advection or dispersion. This process is called intraphase transport. At the same time, this contaminant may also transport from one phase to another phase, which is known as interphase transport. Interphase transport may happen in all directions between the 3 phases. From soil to water, from water to air, from air to water, from water to soil, from soil to air, from air to soil. The direction of interphase transport is greatly affected by both the subsurface environment and the contaminant's physical, chemical, or biological properties. Among different properties of any contaminant, volatility indicates the likelihood for this contaminant to form vapors, thus transporting from soil to air, or from water to air. To compare the volatility of contaminants, 2 parameters are often cited. The first parameter is vapor pressure. Vapor pressure or equilibrium vapor pressure is the pressure of a vapor in thermodynamic equilibrium with its condensed phases at a given temperature in a closed container. All liquids and solids have a tendency to evaporate or sublime into a gaseous form, and all gases have a tendency to condense back to their liquid or solid form. Vapor pressure relates to the balance of particles escaping from the liquid or solid in equilibrium with those in a coexisting vapor phase. A substance with a high vapor pressure at normal temperatures is often referred to as volatile. As the temperature of a liquid increases, the attractive interactions between liquid molecules become less significant in comparison to the entropy of those molecules in the gas phase, increasing the vapor pressure. When comparing the volatility of 2 contaminants based on their vapor pressures, it is important to make sure that these vapor pressure values are derived from the same temperature. The second parameter is Henry's law constant. By its definition, Henry's law constant relates the pressure of the contaminant in the vapor phase with the concentration of this contaminant in its solution phase at equilibrium. When the same unit are used for Henry's law constant, a larger value indicates higher volatility, whereas a smaller value indicates lower volatility. Maybe you have already noticed the problem. Henry's law constants have been reported in many different units, such as atm liter per milligram, Pascal cubic meter per gram, or kilopascal cubic meter per mole. To compare the volatility of 2 contaminants using their Henry's law constants, it is imperative that the units of these Henry's law constants are the same, and that they are derived under the same temperature conditions. For example, chemical A has a Henry's law constant of 1000 atm liter per milligram, and chemical B has a Henry's law constant of 2000 Pascal cubic meter per gram, both derived under 20 degrees Celsius, which chemical has a higher volatility. For the comparison, let's convert the unit of atm liter per milligram into Pascal cubic meter per gram. Note that 1 atm equals to 101,325 Pascal, 1,000 liters equal to 1 cubic meter, and 1,000 milligrams equal to 1 gram. After the unit conversion, the Henry's law constant of chemical A under 20 degrees Celsius becomes above 100 million Pascal cubic meter per gram, significantly more volatile than chemical B. Following this unit conversion method, we can make sure that the units for different Henry's law constants are consistent before any comparisons. However, we are not done with Henry's law constant yet. Oftentimes, you may find Henry's law constant reported without any unit. They can be dimensionless. Then how can we compare a Henry's law constant with a pressure to concentration unit against another Henry's law constant that is dimensionless? To answer this question, let's understand how Henry's law constants can be dimensionless. For example, under 20 degrees Celsius, chemical B has a Henry's law constant of 2000 Pascal cubic meter per gram, chemical C has a dimensionless Henry's law constant of 1. Which chemical is more volatile? The Henry's law constant of chemical B could be perceived as, if we prepare a solution of chemical B with a concentration of 1 gram per cubic meter, then the vapor pressure of chemical B in the gas phase at equilibrium would be measured as 2000 Pascal. The Henry's law constant of chemical C could be explained as, if we prepare a solution of chemical C with a concentration of 1 gram per cubic meter, then the vapor concentration of chemical C in the gas phase at equilibrium would be measured as 1 gram per cubic meter. If we can find a way to convert this vapor pressure 2000 Pascal into the vapor concentration in grams per cubic meter, then we will be able to convert the Henry's law constant of chemical B into a dimensionless constant. Is there such a method? The answer is absolutely yes. The ideal gas law, PV equals to nRT. In this equation, P is the vapor pressure exerted by the gas, V is the volume of gas sample, N is the number of moles, R is called the gas constant, and T is the gas temperature. If we rearrange the ideal gas law, we will have N over V equals to P over RT. In this new equation, N over V is also known as the molar concentration. If we multiply both sides of the equation by the chemical's molecular weight, we will be able to convert this molar concentration into a mass concentration. Now that we have gas concentration in mass per volume on the left side of the equation, and we have the vapor pressure on the right side of the equation, if we know the vapor pressure, we can calculate its corresponding vapor concentration in mass per volume. Vice versa. Now let's use this method to complete the comparison in the previous example. We will need to convert the vapor pressure of 2000 Pascal into an equivalent vapor concentration in the unit of gram per cubic meter. Here we have pressure P equals to 2000 Pascal. We have temperature T equals to 20 degrees Celsius, that is 293 Kelvin. What would be the value of gas constant R? If we look it up online, we will find that gas constant R comes in many different units. Theoretically, we can pick any of these units and work on the unit conversions later. Practically, being able to choose the right unit for gas constant R can help us simplify the subsequent calculations. To choose the unit for gas constant R, let's compare the units on both sides of the equation. Since on the left side of the equation we have gram per cubic meter, it is expected that the same unit will be derived on the right side of the equation. Hence, the unit of the gas constant R should have a unit of cubic meter Pascal over mole Kelvin. As a result, R equals to 8.14472 cubic meter Pascal over mole Kelvin. As we substitute the value of R into the equation, we now can convert the vapor pressure P in the unit of Pa into its corresponding vapor concentration in the unit of gram per cubic meter. Therefore, if the solution of chemical C has a concentration of 1 gram per cubic meter, its gas phase vapor concentration at equilibrium should be 82.1 grams per cubic meter. Consequently, the corresponding dimensionless Henry's law constant is 82.1.